Okay, this is just a short chapter on effects of climate change on non-infectious waterborne diseases. So you can get sick from this, but you cannot transfer these toxins or impacts of waterborne diseases to others. So this is mostly corresponding to warming, acidification of water bodies, including the ocean and the freshwater bodies, and how they are influencing harmful algal blooms, oxygens, acidification, and so on. We know that 93.4% of the additional energy trapped by increased greenhouse gases and other warming created by land use change, etc., is being taken up by the ocean. Atmosphere keeps about 2.3%. It's a very low heat content, low density fluid, which doesn't keep much heat, as you know, for a long time. Continents are taking up 2.1%. Glacier ice caps are melting, using up 0.9%. Arctic ice is melting, taking 0.8%. Greenland ice sheet, Antarctic ice sheet, and so on. Of course, these are estimates, but this number of more than 90% going into the ocean is pretty well known. Looking here at a shorter time period of 1960 to about 2015 or so, we are looking here at ocean heat content in the top 700 meters, deeper ocean from 700 to 2000 meters, and then the total heat change in heat content in terms of 10 to the 22 joules of land plus ice plus atmosphere. So with respect to the base period, which is probably from 1960 to 1990 or so, we can check it. But the main point we want to see is that the heat contents with the baseline, with respect to the baseline, started to increase in the 1970s, and you can see that the top 700 meters of the ocean have acquired enormous amounts of heat, and the deeper ocean is now getting warmer and warmer as well, and of course land, ice, and atmosphere continue to accumulate heat corresponding to their own heat contents and storage. Of course, ice is melting, using up the heat content, which reduces the reflectivity of the shortwave, reduces albedo, and more energy is trapped into the system, which further warms and further melts the ice and the glaciers, as we know. But the ocean warming itself not only is bad for all the living things in the ocean, but it also tends to reduce oxygen concentrations, called deoxygenation, because the gases that dissolve into the water depend on temperature. The solubility depends on temperature and pressure. Warming the temperatures reduces the solubility, of course. And of course, ocean also takes up about 30% of the total carbon dioxide that's being emitted by the human beings. Obviously, we are accumulating a lot in the atmosphere, as we keep seeing in the Keeling curve and other data, where we go back in time to ice cores and look at the change in the atmospheric concentrations of carbon dioxide in terms of parts per million by volume, which has been increasing since the Industrial Revolution. And there is various other components like land cover, which take up 30%. To jump to the impact of these warmings on harmful algal blooms, essentially that means these are phytoplankton that produce some kind of a toxin, or they produce substances that are toxic to human beings. They are obviously not trying to produce toxins to us. They are trying to survive on their own, but our body reacts negatively to it because they are not getting any feedback from us saying this is not toxic enough, make it more toxic. We are not going back to the water body and providing a genetic signal for making them toxic to us. It's just a coincidence. This is global distribution of lake bloom intensity trends, showing that peak summertime bloom intensity has increased since the 1980s. The map shows bloom intensity trends for all 71 lakes studied for the period of 1984 to 2012. Colors and symbols indicate whether the bloom intensity decreased in bloom downward pointing triangle and increased with red pointing upwards, and whether the trend is statistically significant. So there are significance values given here. Less than 0.1 means more than 99% statistical significance, or less than 99%, and so on and so forth. But the main point I would note is that there are lots of places where there are decreasing trends in the intensity of the blooms, and there are many places where there are increasing trends, and the point really is to see which of these are harmful to human beings. Because the bloom intensity also depends on human activity, the runoff, nutrient loadings, urbanization impacts, and in addition to warming, those are all the things that will matter. For example, the agricultural runoff, nutrient loadings, and so on and so forth. There are cyanobacteria and mycobacteria in freshwater bodies that produce cyanotoxins and microcystins and so on, which are harmful to human beings. So the question is, what is happening to them with warming and other human activities like land use change, agriculture, urbanization, and so on. That's a major health concern, but the data tends to be very, very sparse to make too many conclusions, even though now there are many regions where the data is coming in to show that there are indeed increasing harmful algal blooms associated with warming, acidification, damages to coral reefs, and deoxygenation, and so on. Sometimes they just tend to compete better when there is a bloom of when there is a excess supply of nutrients, like in eutrophication. I think you all know what eutrophication means. There is a huge input of nutrients. There is a big phytoplankton bloom. The bloom doesn't get eaten up by the zooplankton, so when it dies and sinks, the microbes respire all that dead material and use up the oxygen, creating hypoxia and anoxia. But many of these phytoplankton blooms, when there is such a burst of nutrients, also tend to be harmful algal blooms, and we will look at some of the examples in a minute. Okay, so I will leave this podcast here and make the rest of the content of this short chapter into the next podcast. Okay.